Seva Shneer. Seva comes from initially from Novosibirsk, and even north of Novosibirsk, not far from Sobut, what's the exact place? Okay, so if you want to learn more about Siberia, so please ask Seva. So Seva studied in Novosibirsk in the Department of Mathematics. Then he did his PhD with Sergei Foss in Heriot-Watt University, and then got a position thereafter. He did his postdoc in the Netherlands, right? Yeah, and Switzerland with Patrick Léon. And now he's in working in the same department as Sergei Foss in Heriot-Watt University, and he used to visit often and was interacting with Charles Bordenave on Aloha, right? That's dynamical systems and quite nice stuff. Lately, so he's a probabilist, broadly speaking, with interest in stochastic stability. And lately he got very active with Sasha Stolyar, who is now at UIUC, who was at labs actually for many years, working on utility-maximisation schemes. And he will today lecture on this topic. I forgot many things that he did. Okay, thank you,
Francois. Thank you for the introduction and also for the invitation. It's nice to be here. Nice to visit again. As Francois said, I've been working with Sasha Stolyar from UIUC a lot lately, and we've already written 4 papers on failed attempts to solve one problem. So we still haven't solved the problem we wanted to solve. While trying to kind of simplify it and look at it from different angles, we managed to write 4 papers. So I don't think I'll have time to talk about the problem we originally wanted to solve. But maybe tomorrow, for those of you who are there, that work is closer to the original problem. Here we went way too far off. So anyway, I'll talk about some service rate allocations, describe their utility maximizing properties, or properties of maximizing some utility functions, and then also talk about what you can do with those properties. So, this doesn't work. We're going to have a few times. Right, so the talk is non-linear, so I've decided to help myself and all of us with some outline. So I'll start with a review of the well-known alpha fairness concept. Everyone has heard of alpha fairness? I'm just trying to gauge how fast I do. Okay, I'll go slower then. So I'll talk about what's called alpha fair allocations of rates, and then I'll take a complete detour. So then I'll sort of ask you to forget about alpha fairness and look at our motivating example. Example of a network that we studied, which will look like it's not connected to alpha fairness. And actually, I'll talk about another motivating example, and I will say this not only because Francois is here and Francois participated in this work, but I generally think this is a better motivating example. It's not just because Francois is here. Okay, so Francois and his co-authors had another motivating example which we discovered was very close to what we considered. So therefore we have 2 motivating examples, very similar. And then at that point I'll sort of connect this to alpha fairness, both these motivating examples, and hopefully also motivate studying a framework which is more general than alpha fairness. Then I'll describe this general framework, and finally talk about our results, which will concern this general framework, as well as referring back to our motivating examples. Okay, so what these general results will mean for our particular problems. Okay, so not linear, but hopefully I've explained that they're not too good. Okay, so alpha fairness. Assume this is a flow model of a network. So we have these blue circles here our links, or servers that will be transmitting some packets. Okay, and these lines of different colors are different flows going through this network. Okay, these flows can take different paths. So the red flow, for example, goes like this. The blue flow does something really strange. Okay, and we also have this yellow flow. Okay. So this means that packets from the red flow will need to be served here, here, and here. Okay. And we assume that this model, this model assumes that packets go through the network so fast that you don't actually see them going from this link to this link. You can assume they're served simultaneously at all three links that it's served. So all the packets from the red flow will be served here, here, and here, in fact, simultaneously. Okay. Each of these links, of course, has some capacity. So we can say that server J or link J has capacity Cj. Okay. And this Cj needs to be somehow shared between all flows that traverse this link. Okay, so this link will have capacity C1, so it needs to share that with red packets and red flows. Okay. And so on. And of course, you can't give more capacity than you have. So we have a service rate, the red flow will enjoy service rate psi1, yellow flow will enjoy service rate psi2. Psi1 plus psi2 can't be larger than C1. Okay. So, at all times. Okay. So we can encode this in this linear constraints. Doesn't matter. So I hope you get the idea, right? So you need to share service rate among everyone who is using that resource, and you have some constraints on this service rates. Okay. But this is the sort of typical scenario where rate allocation was studied. But we can also think more generally. Okay. Let's say we have n servers that interact in that they sort of somehow have to share service between different customers. We have arrival of jobs into server I, which will be +1 process with break down the I, continuous time. Instantaneous departure rate from server I will be some function, which you denote by psi I, that will depend on the state of the entire system, okay, on queue lengths at all servers. So not only how many customers there are in QI, but not only how many jobs there are in QI, or whatever we call them, customers or jobs, but also how many jobs there are in every other queue. And this vector psi, this vector of departure rates, is something you can choose. It's something the system can choose. It's subject to this rate allocation, but in such a way that these vectors need to be from some set C, which summarizes the constraints of the network. Okay. So in my first example here, psi needed to satisfy this, but in general you can think about other constraints. Okay. You need to choose psi belonging to some constraints at C, and you want to do it in a smart way. And what we'll talk about as being smart is we want to keep the system stable for as many arrival rates as possible. Okay, so lambda i's, we want them to be from as large set as possible, but still keeping the system stable. So this is continuous time. I will also need to define the system in discrete time. So what I consider by discrete time is the time is slotted and every service time is equal to 1 exactly, so everything happens at time instance 0, 1, 2, and so on, and every transmission will start at the beginning of a time slot and end by the end of the time slot. And if I denote by xik, the queue length of qi at time k, then how does this evolve? Well, what we'll have by time k plus 1 is what we had by time k plus what arrived minus what departed. Psi ik, these arrivals, we assume them to be IID as always, and they'll have a finite expectation which will be known by lambda I, so that sort of mirrors our boson arrivals assumption. Now what departs? So in everything I will consider, what departs can only take value 0, 1 in the time slot. Okay, so each queue can only serve one customer. In the time slot can serve more, but sometimes one serve. Sometimes one serve anyone. I will denote by psi ix, again, rate of departures. So in continuous time, this was exactly rate of departures. Now I have to sort of think about it as rate of departures. Sort of what leaves on average. Okay. So expected departure or probability that there is a departure, which is the same thing in this case. Okay, and that will depend on x. And that will be what's subject to my choice. Okay. So again, I'll have some constraints. And I'll be from these constraints, I'll be choosing this expected departure. So similar to continuous time, it's actually, I'll make this comment later on as well, but I'll do it now. So continuous time turns out to be slightly more difficult than, discrete time turns out to be slightly more difficult than continuous time in this setting. Because in continuous time, you know, if you look at a small time interval, you will at most have one event. Whereas in discrete time, you don't have these small intervals, you only have your interval of size 1, and lots of things can happen. You can have lots of arrivals, you can have lots of departures, and so on. So you need to deal with more events in discrete time. So some results in continuous time will require no assumptions, whereas in discrete time you'll need to make assumptions on disk size. You'll need to make further assumptions on disk size. Okay. Right. Now, how do we choose this rate of psi? Okay, that's where alpha fairness comes in. This was developed a long time ago. So the idea is, well, let's choose psi, or vector psi, which is in some sense optimal. Okay. And what's meant by alpha fairness is that psi will be optimal according to this utility function. Okay, so you want to assign rate mu I to qi. You look at how much. So if you then share that rate among all the customers, all the jobs in qi, this is the rate that each job gets, and you have some convex function of this job. Okay, that's utility for each job. You multiply it by the number of jobs in qi, and then you add this up over all modes. Okay. So that's the idea. Let's choose psi from this rate. So if you assume that set C is convex, then there will be a solution. Let's take this as being our rates. So this is for all positive alpha not equal to 0, not equal to 1, sorry. If alpha is 1, then this sort of breaks, but you take log instead of this function. Okay. And so this is the original motivation. You can rewrite it in this form. Okay. You can also rewrite this, what's called proportional fairness, in this form. Okay. In both cases, this will be useful for what I'm talking about later. In both cases, you take psi, which maximizes sum over some function of rates times some function of q lengths. You maximize that over all possible rates. Okay. Right. So this is how you choose psi's. Now, it was proved also a long time ago that this choice of psi's keeps the system stable as long as stability is possible. Okay, so this rates guarantee that system is maximally stable. So what does it mean is that if I have a vector from my constraint set such that my arrivals vector is coordinate-wise dominated by this vector from constraint sets, then I have stability. It's easy to see that if my lambda I is above mu I for all vectors from the constraint set, then I will not have stability. That's easy to see. So this is really sort of the best stability possible. Best stability possible, and alpha fairness guarantees that this is achieved. So system picking the rates using alpha fairness keeps system stable for all arrival rates for which it's possible. This is very good, and I'll make a note. So the proofs, the standard known proofs, are based on fluid limits. And fluid limits are great tool, but to justify fluid limits, you need something like homogeneity of your rates. Okay. And if you, by homogeneity, what you have in these cases is that if I multiply all my xi's by some t. Okay. And I can just take this factor t out, okay, and my optimization probably will not change. Okay. So if I look at t times x, where t is a constant, positive constant, and well, what I'm maximizing is this guy times tx to alpha. Take t to alpha out, I have the same solution. Right? Psi of tx is equal to psi of x. And that really helps justifying fluid limits. Okay, you don't need exactly that. You need something approaching that, but this is certainly a very helpful problem. So that gives you fluid limits. And set C is assumed to be convex, just to make sure that you have a unique solution. Okay. Any questions of fairness? So now let's, as I said, non-linear talk, so forget everything about fairness. Okay. Let's look at the example we started. So we have an undirected graph, we have n nodes which will be transmitters in the network, and there is an H between two transmitters if they interfere with each other. Okay. So having an H is a bad thing. And we assume that interference is sort of 0-1 interference, so if you are a neighbor of somebody, you will never transmit simultaneously. If you're not, then you can always transmit simultaneously. Okay. And it will also assume that transmitters can sense what's happening near them, so if my neighbor is transmitting, I will actually hear it and I will not transmit. So they will never be in conflict. So I will never start transmission. So we assume that time is discrete. In our original model, time was discrete, therefore I had to introduce this discrete setting before. And we have this psi k new arrivals at node I, this IID over time with expectation and I, so that's standard. Okay. Transmission time is 1, which is also standard. Now how do transmissions happen? Okay. And by the way, this is, I know this is a bad example. This is not how networks work, but as I said, there will be a better example later, so please bear with me. Okay. So I'll explain this example. So for node I, we denote by ni its neighborhood, which will contain of all the actual neighbors plus the node itself. Now, at the beginning of each time slot, every message who is now in the system, so every job who is now in the system, not every node, but literally every job, will get a priority, okay, which will be assigned at random. And if there are n messages, jobs in the system, then priorities will be assigned from 1 to n as a random permutation. Okay. And we'll be saying that priority 1 is the highest, n is the lowest. Okay. Now, a message sitting at node I will be transmitted if and only if it has the highest priority in its neighborhood. Okay, so if I beat all the other messages sitting next to me in my queue and all the messages sitting in my neighbor's queues, then I will transmit. Otherwise, I will not. If there's anyone with a higher priority than me, then I will not transmit.
All neighbors have the same permutation at the same time, or priorities?
Sorry?
All the nodes in the neighborhood, they have the same permutation?
No, so you literally look at all the messages. Okay? You have n messages in the whole system, and you give them priorities from 1 to n. So in this time slot, you give them priorities from 1 to n. So you'll never have the same priorities. You just assign priorities from 1 to the number of messages, and we do it random. Okay?
No, about the other nodes as well.
About the other nodes.
So other nodes will be having some messages and
yeah, so not messages only in my node will get priorities.
okay.
Every messages in the entire system will get priorities assigned from 1 to the total number of messages in the system. Not in the queue, but in the system. Okay? Right, so this happens in a time slot, in the beginning of a time slot, then who can transmit will transmit. Okay. And then in the next time slot, everything is repeated independently of the past. Okay. So you forget your priorities. In the next time slot, there will potentially be a different number of, there will be not little n, but little n1 messages in the system. You'll reassign priorities now from 1 to n1, and you'll continue this process. Okay.
Create an independent set.
It's worse than that, right? Because
it's not as good as independent.
Yes, it's not a maximal dependency, just an independent
set. And inefficiency comes from the, if you take uniforms, I mean, of having some interfaces that would forbid somebody to transmit.
So I have an illustration in just a moment of exactly this. So it's inefficient, it's not common to observe. Just bear with me, please. Okay, I just wanted to note that this it sort of assumes a lot of centralization, right? There should be some central device that knows exactly who is where and kind of gives them priorities. But it's easy to make this decentralized by losing a small proportion of each time slot. You sort of devote epsilon proportion of a time slot to competition, and you make each sort of message choose a uniform 0 epsilon time and wake up after that time. So if you wake up first, you will be transmitted. So, and then instead of transmission time 1, you take transmission time 1 minus epsilon. So everything is indeed finished by the end of the time slot. So you lose this epsilon proportion, but you make this completely decentralized, apart from having a queue. Whereas, for example, this alpha fairness really requires some central controller because, remember, you need to solve a global optimization problem at each time. So this can almost be made decentralized by losing epsilon, and we just, as mathematicians do, we assume epsilon is 0 and happily continue. Okay, epsilon is of course not 0. Okay, but we'll assume that epsilon is 0, so we'll really be working with these priorities. Okay. Now we're interested in stability of finite networks, or also infinite networks, if I have time for that. Right, this here. So little illustration of 6 transmitters, simple graph. Okay, so this node can transmit simultaneously. This node and this node can. So they could be up to 3 simultaneous transmissions in time slot. Now, assume there are what these rectangles represent jobs sitting there at the beginning of the time slot. Okay, so there are 8 jobs. We assign them priorities at random. Okay, we didn't. I assigned them, of course. Assume you did. Okay. Now this message has priority 1. It obviously beats everyone in its neighborhood, so it will be transmitted. Message with priority 1 will always transmit. Okay. But this message now can't transmit because this one beats it. This can't transmit because this one beats it, and so on. So no one else can transmit. This is why it's inefficient, but that wouldn't happen in the real life because other messages would transmit. Okay. Now examples we forbid it. Right, so this one leaves. Assume nothing else comes. Okay, so we are now down to 7 messages. We assign priorities differently, and we can see that now 3 messages will be transmitted. Okay, so now we are in the most efficient situation. How do we analyze it? Well, if I condition on there being exactly xi messages in node I, and what's the probability that one message from node I beats all other messages in node I and in the neighborhood? It doesn't take a long time to figure out that this probability is given the illustration. So xi guys compete with sum over all neighboring nodes of xj's. One of these guys wins with this probability. Simple. And this probability of transmission is exactly expected number of transmissions because there could be 0 or 1 transmissions only. So this is measured. Now, a better motivating example, as I promised you, it's due to Francois with Abhishek and Sergey. Okay, so they looked at modeling continuous time. They assumed that transmitter-receiver pairs arrive at a certain location according to a Poisson process right under I. Okay, so there's transmitter-receiver pairs which are really close to each other. And all transmission happens simultaneously, but there is interference. So there is no sort of queue or no competition for access to the medium. Everything happens simultaneously, but there is interference. And so if I'm not mistaken, you only looked at Z deep. Right? You can still consider a problem on a general graph. Okay, so again, let an I be this interference neighborhood. Everyone this node will interfere with. So I'll say a little later you have this more general interference model, but I'll comment on that later. So assume there are xi again, so a condition on there being exactly xi of this pairs at location I. Now and every transmission is done with power 1. So the total interference then experienced by one of these xi guys is noise plus everyone who is in the neighborhood is transmitted with power 1 minus 1 because I don't have to count myself. Right, now signal to interference ratio is then 1 over, and I'll just assume that noise is 1. And I just have this. So that's signal to interference ratio. And assuming that you have Shannon rates for transmissions, then each of xi transmitter receiver pairs at node I will be transmitting with this rate. Therefore, from location I, you will have total transmission rate being given by xi times this log, which you can approximate by 1 over log 2 times this ratio. Okay. And lo and behold, up to this constant, we have the same ratio as we had in our non-motivated example. So, same ratio, and so Francois Abhishek and Sergei considered more general model for interference. So our results can handle more general models for interferences as well. And I made some comments when I talk about the results, but I'll just say now as well. I'll stick to these ratios for the talk just to keep things simple. You can consider more general rates. This is the sort of typical example that really represents everything we're interested in, everything we need to know. Okay. So you can generalize it later. Okay. So we are back to the same rates. We can consider them, but there is also this approximation here. So it would be nice to say something about these rates actually rather than the approximations. So this we can't do. But what we can do is we can look at rates of this one. So another approximation, at least to keeping the log there. So we can't deal with this ones exactly. We can deal with that approximation, or we can deal with that approximation. Okay. Any questions? All right. Now let's just forget about motivating examples. Right? We can just consider discrete or continuous time. Both are interesting. Can consider arrival intensities of lambda I, whether it's a Poisson process or just the expected number of arrivals in discrete time. And we consider departures being given by this, which I'll call ratio rates, just for the purposes of this talk, or departures governed by this, which I'll consider log ratio rates. So it doesn't matter where it comes from, let's just consider this system that works like this. Discrete or continuous. Okay. So this motivation part finished, so let's look at these rates. And now, so say that we can consider more general rates as well, so representing more general interference structures. And finally, I'll sort of come back to fairness, which I started with. So the analysis we did is based on this very simple observation. Once you make it. So let's talk about ratio rates first. This exact xi over sum of xj's. Okay. So let me look at this set. Okay, so this is the set of all vectors such that there exists vector P, which will give me a combination of Q lengths, which will be the structure of Q lengths, such that mu I, at every point I, is dominated by a departure rate from this particular configuration of Qs. Okay. This will be my natural candidate set for stability, because if I know that lambda I belongs to the set, then I know that at least there is one combination of Qs where everything drains from the Qs. Okay. So if my lambda is not in this set, then I really don't expect stability, because in every combination at least something, at least one Q grows. Absolutely every combination. Okay. Combination of Qs. Whereas in this case, there's at least one combination where what comes to every Q is smaller than what leaves every Q. It turns out that that's the key observation, and it's in this lemma. So if I take my ratio rates, it's exactly my ratio rates, which by the way belong to the set naturally, because I can take pi to the xi. Therefore, these rates belong to the set naturally. Okay. So it turns out that these rates are actually optimal in the sense of alpha fairness with alpha equals 2, okay, or in the sense of this particular utility function. Okay, so if my utility function is mu I over xi to minus 1 minus times xi, that happens to be my utility function. If that happens to be my optimization set, and these rates are the best. Okay. Or I can rewrite this in this form, which is more convenient for formulators. So it's something of x times something. Okay. So very simple observation, and it's quite easy to prove as well. And again, you can handle more general rates here, so you just make the set more general, the rates more general. It just works. And this is just a particular case of alpha fair allocations if alpha equals 2, which is seems quite surprising, at least to me, because remember in our discrete time example, we did something that could be almost decentralized, could be made almost completely decentralized. But it turns out to optimize something global. So this is surprising, this is interesting, I think, on its own. But also it gives us stability for P. Because we know that alpha fairness gives you stability on any graph. So therefore, we know that if lambda is sort of strictly within the set C, then I have stability. It follows almost immediately, because remember, in alpha fairness, one assumes that C is convex. The optimization set is convex, this set is not convex. So you need to look at the proof and see convexity is not actually needed. But convexity is needed for in alpha fairness to actually make sure that this solution exists. Because there you need to take phi to be equal to Rmax, right? You're solving something. So all we do here is say that phi belongs to Rmax. Rmax may contain more points. So we don't need convexity, and you can see in the proof of alpha fairness, the fact that alpha fairness leads to stability, that you don't actually need convexity. Follows almost immediately. Okay, so for a finite graph, we actually solved all our stability problems by just this one key observation, by little observation. Now, what if I want to say something about more interesting rates, which are log? I think they're more interesting. You can do something very similar. Now, your set is, again, the same. So, set of vectors mu, such that mu I is smaller than departure rate from qi for some configuration of q's. That's just my departure rate again. So, set C is the same sort of philosophy, the same idea. Your arrival rate is smaller than your departure rate for one combination of q's. Then psi, so again, this particular rates are again optimal. But now with respect to another utility function, and g is still x squared, so it's still the same as before. H is now rather different from -1 over 1. So stability So we have optimality, so our rates are optimal in some sense, but we don't automatically get stability from our fairness. Okay, so that's one motivation to look at utility maximization, which is more general than alpha fairness. But we probably don't really need another motivation. We can just say, well, can we look at something, utility optimization, which is more general than alpha fairness? And that's exactly what we did. Okay. So now, assume that my rates should be phi, an upside. That's the limitation. So assume that I choose my rates, which will maximize some utility function. Okay. This is where it comes in useful that I was rewriting everything in terms of something of x times something of mu. So let me try to look at more general functions g and h. Not power functions given by alpha fairness. Let me assume that. Let me see how much more general I can make these functions. Okay. I will not assume that C is convex. I will assume that it's coordinate convex and compact, like we had in all our examples there. And so it turns out we can do the following. We can go this far about the functions h and g. So h, function h, we only require it to be increasing, differentiable, and complete. Okay. And this needs to be defined for all non-negative rates. So in alpha fairness, h looks like this, all log. You can see that they all strictly increase in differential and concave. So we can handle more general functions h. Now what can we do for function g? First of all, we will not even need it to be defined for non-integer numbers, because we will not use fluid limits. G acts, so in optimization, G acts on Q lengths. So in principle, it only needs to be defined for integer numbers. One takes x to power alpha in alpha fairness because proofs use fluid limits, therefore everything gets scaled, and you need this function to be defined for real numbers. We will not look at fluid limits, so we won't even need it. Okay, so we just need it to be defined for integer numbers. And we'll require that it's strictly increasing and sort of long-tailed. So this property just means that function g, as long as it's not crazy, all we need it to be is grow. It grows, it's strictly increasing, but it needs to grow slower than exponential. If you have an exponential function here, this doesn't go to 1 anymore. But anything slower than exponential, the ratio will go to 1. So in alpha fair allocations, g is taken to be y to alpha, which of course satisfies these properties. But we can also take anything like looking like e to log x to some power, or e to x to beta, where beta is smaller than 1. So really anything that's reasonable but slower than exponential. So we can prove now the stability result. So the result will not be surprising at all. The fact that we can deal with more general functions just comes from us not using fluid limits. Okay. This comes at a cost in discrete time. So in discrete time, we have to assume that psi is a Bernoulli. So arrivals are only 0, 1 in general. As in continuous time, we don't need to assume anything else, because in continuous time, you kind of already assume Bernoulli arrivals. If you look at a small time interval, you have a Bernoulli arrival. So that's already done in continuous time. In discrete time, it's a bit harder, so not according to fluid limits comes at the cost of discrete time. Okay. So the result is not surprising. As I said, if lambda is strictly within this set C, then you have stability as is the result of fairness. And we can now look at more general functions G and H. Proof is just one Lyapunov function that works in one step. Okay. And it's given by some derivative of h at point nu and discrete integral of g. And even the Lyapunov function, if you've seen alpha fair proofs, you will not be surprised by this Lyapunov function. Essentially, it's pretty much the same Lyapunov function is used there, but this is not discrete integral. This is actual integral. Okay. So we can handle more general functions h and g, but the fact that we have a so this actually, this actually already solves our stability problem for log ratios. Remember, log ratios were optimal with just different function h. Now that function h satisfies all these properties, so we solve the stability problem for log ratios like this. Okay. The interesting thing is that by not using fluid limits and by coming up with a one-step Lyapunov function, we can actually say more about the stationary regime. If you have a Lyapunov function with fluid limit, you can't necessarily get some bounds on stationary measures. But if you have this one-step Lyapunov function, sometimes it works. And it turns out to work here. So if you have the right Lyapunov function, and you know that there is a stability regime, right? You can then just say, well, instability in the stationary regime, my distribution of x k plus 1 is the same as distribution of x k, discrete x. And I can just take the same Lyapunov function f, take the expectations on the left and on the right, and equate them. And often that leads to something interesting, and it does in this case. So in this case, we can prove also not only stability, but the following result. So assume that we have this lambda strictly belonging to set C. Therefore, there is this little epsilon such that lambda I is smaller than the ith coordinate of the vector from set C minus epsilon. Then we have the following bound on the moment of x, on g sort of moment of x, of the expectation of g of xi, where g is the function which figures in my utility function. So that's g of xi. And on the right here we have this capital delta, which is the discrete derivative of g. So this is probably somewhat interesting, but not very useful unless we make further assumptions on the function g. So if
xi is a steady state?
Yeah, xi is steady state, sorry, yes, thank you. So so all capital X's here are random elements that have distribution which is equal to the stationary distribution. So in stationarity, expectation of g of xi is bounded by something involving expectation of a discrete derivative function.
So this would prove existence of moments typically for the stationary distribution of the induced.
Yeah, so usually for existence of moments with this function g. So this kind of looks somewhat not very interesting, but if you make further assumptions on function g, then we can get some very precise bounds for our stationary moments. So if we go back now to alpha fairness and see what else we can get with this new Lyapunov function, so take g of x to the s to alpha. Then you can actually make more sense of these inequalities. And I'll use this particular example which we had before, where g was square function and h was minus 1 over y. So that's exactly this alpha fairness with alpha equals 2 that we observed for our ratio rates. This is not a random choice of function, but it's exactly this utility function we had for the ratio rates. Okay. So I take g to be y squared, h to be minus 1 over y. So because I've made further assumptions on g, I can relax my assumptions on size. So in discrete time, I only need to assume that the third moment exists rather than assuming the null arrivals. That's maybe not that interesting. So again, nothing else in continuous time. You've assumed everything you wanted already. So now we assume that stability holds. So we fix this epsilon, the gap size. Then for stationary regime, so for xi's representing stationary distribution of the q at node I, have this inequality, which now involves second moments for xi's. First moment. So only, well, x is of course discrete derivative of x squared, so it's not entirely surprising there. So this is just essentially rewriting the previous theorem in explicit function g and h. But now, so this a, I, and b are they're not even saying there exists this constant such that this holds. You can actually write out a and b exactly. Okay, so I don't expect you to kind of read this, but this is a very explicit bound. Okay. So first of all, it says that moments exist, second moment exists. That's not surprising because for alpha fairness, even exponential moments. That's not surprising. But what's interesting is that this bounds are very explicit. So we have exact A and B. Now, this is, so I'll talk about this in a moment, but preliminary, assume that everything is symmetric. Okay, so assume I can come up with a very symmetric network where all these new i's are the same and xi's will all have the same distribution. Okay, so I will come up with that model just now. Assume I can. Okay. Now the left-hand side looks like n times some constant times expectation of x1 squared. The right-hand side then, so ai's, assume I can make them all the same. So I just assume that xi's will have the same distribution. Okay. So then here I will have n times some constant times expectation of x. Okay. And what is b? Well, b is also sum over I of something that if I make i's to have the same distribution, all of these fractions are the same. So b is also n times some constant. So I have n times constant times expectation of x squared smaller than n times constant times expectation of x plus n times constant. Okay, so n just cancels out. And I will have a bound on the second moment of x, which does not depend on n. Okay, which does not depend on the size of the network. How can we use this? So how can we use this? This is now, so we sort of finished with the actual results. We just see how we can use them in some particular cases. So I will assume that my servers are located on a line, okay, on Z, and I'll be interfering with my nearest neighbors. Neighbor to the left, and neighbor to the right. My array becomes this, my service array. Now, again, we can consider more general settings, but let's stick to just these for the talk. I'll assume that xi's are ID, as I said before, so I'll just assume that my xi's are ID not only in time, but also in space. Okay, so they're also ID in time. All lambdas are the same. Okay. So then, so remember my set C was sort of strange collection of all mu's such that mu can be dominated by service rate for some configuration. Now if I assume that this is my service rates and all lambdas are the same, then for lambda to strictly be in the set C for the vector is equivalent to this one of these coordinates in smaller than a third. So for vector lambda consisting of the same entries to belong to that strange set C is actually equivalent to one of the coordinates is smaller than a third. So my sense of the strange set C in this particular case. Okay. That of course doesn't depend on the size of the network. Okay, so now I look at the network in minus m and consider it as a circle. So join minus m and n. Okay. And of course we have our stability result shows that if lambda is smaller than a third, Then we have stability for any n. So lambda small confer has it. Okay, so then I have a stationary distribution for sort of, I should say for node 0, say. Okay, so x0n, for example, would be stationary distribution for q0 in the network, which consists of this segment minus nn seen as a circle. Then what I said before holds, right? So I grow my network. The network is symmetric, but my bound on the second moment of x doesn't depend on n. So there is a constant such that this holds for any n. And after that, so I kind of sweep a lot under the carpet here. I knew there wouldn't be time. So you can use, essentially this shows that stationary measures are tight. Therefore, you can grow your network and construct a stationary distribution for the infinite line. That's the use of our bound. In fact, it's explicit, so we can sort of write down all the coefficients and see that n's will cancel out, and we have this constant here not depending on n, so which gives us tightness, which allows us to construct a stationary measure for the infinite process. Okay. We can do the same for log ratio rates too. So not only for ratio rates, but also for log ratio. Am I out of time?
A few more minutes.
Okay, so this part is done. We understand everything well here. Everything is due to this utility maximization properties. Now the other part is something we don't understand, but magic works in some cases. Okay. So assume I now have what's called a multi-hop network or Jackson type network where after being served somewhere, job may move to its neighbor. Okay, a message may move to its neighbor. Okay. So we'll just I'll just stick to line topology, especially now that we don't have time. We can handle a d-dimensional lattice, not a general graph, just a d-dimensional lattice. Okay, so arrivals are id over time and space, so everything is symmetrical. Expectation of psi is now lambda times q, where q is fixed. Second moment of psi is finite. Service rates are exactly what we had just now. I interfere with my nearest neighbors. Now, if I was served at a node, I will leave the system with probability q, which is the same as q here. Or I will, with probability 1 minus q, I will not leave, and then I will go to left or to right with probability half. Okay, so if I don't leave, I perform this simple random walk. If I leave, I leave. If I moved, then I will need to be served by the node. And everything is independent of everything else. And the fact that the Q is here and the same Q is there just ensures that the actual work that each message brings is exactly lambda. Q is there for just convenience, because then I'll need to be served a geometric number of times with expectation 1 over Q. So lambda Q times 1 over Q is lambda. This is all fine. Okay, now, of course, these rates are still alpha fair, but alpha fairness does not guarantee stability in multi-hop networks. So we can't, there's still utility maximization, but we can't directly get stability from utility maximization in this setting. What works, however, is just a simple Lyapunov function, which is a sum of squares. Sum of squares guarantees that lambda smaller than third gives you stability still in this case. So lambda is still the expected arrival that each job brings. So third here is not surprising, but how it works, we don't understand this. There is a Lyapunov function which just works. But again, there is a Lyapunov function, so you can take your stationary regime, take the expectation of x squared at time k plus 1, equate it to expectation of x squared at time k, and get bounds on the first moment. So there's very precise bound on the first moment. And again, that of course means that if I start growing now the network, the right-hand side doesn't depend on n nicely. Therefore, measures are still, stationary measures are still tight. Therefore, I can construct stationary measure for the process. And I will stop here. Thank you for your attention.
Questions? Maybe I should have asked this question at the very beginning. So to understand the stability condition is that the vector of rates should be dominated by the vector of some proportion of when the Q lengths are involved, right? These Q lengths depend on the input rate. So this is some kind of implicit stability condition, right? That's
so which one do you mean, the hours?
Yeah. This is just if my understanding this is correct. So these PIs, which are Q lengths in what system? System fed by some.
That doesn't matter. So forget about Q lengths completely, right? So vector mu will belong to the set as long as I can find some vector p such that mu I is smaller than phi I at vector p. The Q lengths explanation is really just a way of describing this. So what I'm saying is I have my rates. I have my rates phi. Okay, these are my rates. And I'm saying that C will consist of all vectors mu such that mu I will be smaller than phi of p, phi I of p, for some p. So if I can find a vector p such that I then apply functions phi to it, I will dominate all mu i's, then my vector mu will belong to the set. So you can define it anyway, right? My explaining P as configuration of Q's is just a way of describing this set. It's not, P is just a vector. Then we can think of it, what does it mean for a vector to belong to the set? Well, it means that if I think that mu's are arrivals, and P is this particular P is the Q state, then arrivals are dominated by departures. And that's just interpretation. Definition is just.
Could you go back to the multi-hole case? So, I mean, you say you go left or right, so the population then is kept, right? So.
No, population is kept if I haven't left. So I leave the system in probability Q.
Okay.
The probability
so
Q I leave.
Geometric number of steps, and so the stability condition should be the so lambda Q less than 1/3.
No, so arrival is lambda times Q.
Okay.
Now so we change this now,
okay.
and each job needs to be served geometric number of times with expectation 1 over Q.
Okay.
So the actual work that comes is lambda.
And so how does this bound compares with the exact formula that we always again? So because we have the
so you have Q. So you have Q which is equal to
Q is equal to 1. So
Q is equal to 1.
And so I'm trying to see how far you are from the.
We should probably check that. So this is this is discrete time. We have continuous time results too. So that's that disappears, right?
Yeah.
Lambda minus. We should check that. Yeah, thanks. You just have Q equals 1.
The denominator is the right order, but the question is for the numerator.
Yeah, a third minus lambda you definitely have. Yeah, you should check that. Thanks.
Okay. Ok, c'est Sylvain.